Buenas tardes a todos los asistentes a este Simposio Internacional de Vulnerabilidad y Ciclo de Vida de las Estructuras. Les damos a todos ustedes la bienvenida a esta tercera conferencia de este simposio. El día de hoy estará presentando su conferencia magistral el doctor Bruno Briseghella. La plática que él nos dará trata sobre la extensión de la vida de servicio de puentes a través del uso de materiales y tecnologías innovadoras. Es para mí un honor presentar al doctor Bruno Briseghella, quien es profesor titular de la Universidad de Modena y Reggio Emilia en Italia, también profesor distinguido en la Universidad de Fuzhou de China. En el periodo 2015 a 2024, fue el primer decano de nacionalidad extranjera en la Facultad de Ingeniería Civil de una universidad de China. Es autor de más de 130 publicaciones en revistas indizadas y conferencista invitado en más de 50 eventos académicos internacionales. Especialista en diseño, mantenimiento y sostenibilidad de puentes, así como pionero en el uso de materiales y técnicas innovadoras en estructuras. En el año de 2022 recibió el doctor Bruno Briseghella el premio a logros docentes en Fujian, China, y en 2023 el premio internacional de cooperación de ciencia y tecnología. Sus contribuciones han permitido el desarrollo de obras de gran importancia, como el puente integral más largo del mundo en Italia y el puente de arco más largo ubicado en Vietnam. Bueno, como ven ustedes con el currículum que acabo de leer, es verdaderamente un profesor con una experiencia muy grande en el área de investigación y desde luego también con aplicaciones muy claras a la práctica profesional. It's an honor for me to introduce Professor Bruno Briseghella, who has an extensive background in bridge and earthquake engineering research. I would like to particularly thank him for participating in this symposium, especially considering the time zone difference in China. He is right now in China. I apologize for the early wake-up call for his lecture. Thank you very much, and I hand over the microphone to you, Professor Briseghella.
Thank you, Jose. Thank you, Professor Haro, for your really very nice presentation. I would like to thank you all to listen to my presentation. I hope you can see my screen now. Is it working? Do you see my screen?
Yes.
Okay, so today I would like to discuss about a topic we are working on from some years. So which techniques can we use to extend the service life of bridges, and also how we can consider to rehabilitate our existing bridges, or to design new bridges with a longer life, but considering not only the situation at the moment in which you are going to rehabilitate the bridge, but also considering what will happen, the scenarios that can happen in the future. But let me acknowledge also my co-workers. All this research is done inside the National Research Center of the Ministry of Science and Technology. We have established some years ago in my university in China, in Fuzhou University. And inside the Sustainable and Multi-Hazard Resilient Bridges Structure Research Group, that is established between, in my university, between some Chinese university and also many European university, particularly from Italy. But let me introduce the contents of this presentation. after an introduction where I'd like to show you the dimension of the problem, I would like to show how we can consider assess the cyclic behavior of aged reinforced concrete bridges and considering the effect of chloride. We know that many of the bridges built in most of the countries, they have already overpassed the design life. And so we need to, of course, take into consideration the effect of the corrosion. And I will introduce techniques we have recently developed. Another point is how to use static incremental method as an incremental model pushover analysis for the seismic assessment of corroded, damaged, reinforced concrete bridges. And I will show you something we have done in the last years. After the assessment, we need to do a little bit a step forward. So how can we rehabilitate the reinforced concrete bridges, and in particular the reinforced concrete bridge column, and how we can also apply high performance material, in particular ultra high performance fiber reinforced concrete that are material that from one side are still expensive, but from the other side that allow us to have a high strength material, but also, and this is from my point of view even more important, a high durable material. And we will discuss about it. After, I will show you also how we can address with the problem of durability of expansion joints and bearings. We know that most of the time expansion joints and bearings are the most sensible element of our infrastructures due to aged problem. So we can, in this case, we can also try to use integral abutment bridges, and we have done a lot of research and also application on this typology. Before draw my conclusion, I would like to introduce you a concept that for me it's important. We are always discussing about seismic hazard map. So my question is, can we use the same concept to propose some probabilistic corrosion hazard maps that can help us to assess the existing bridges, but also to design the new bridges? So we have proposed a method to do it. It's still the first step, but from my point of view, it's very promising. So what is the problem with the bridge maintenance and service life aspect? If we go to see the situation, for example, in US, on the more than 600,000 bridges in the National Bridge Inventory, the NBI, the average age of bridges is more than 44 years. And more or less the 42% of the bridges are at least 50 years old. more another data that can give us the dimension of the problem is that almost the 7.5% of the bridges are classified as structural deficient, so they need to be rehabilitated. And this bridge rehabilitation cost was estimated to be more than 120 billion. So this gives you the dimension of the problem in US. Regarding Europe, we have around 1 million of highway bridges. And most of the bridges have been built after the Second World War. So it means in the 60s and 70s. And when they were designed for 50 years design lifetime. Now we usually consider to have a design lifetime of 100 years, but in the community, in the bridge community, we are opening a discussion to extend the design lifetime. I clearly remember a lot of discussion inside, for example, the International Association for Bridge and Structural Engineering to extend it to 200 or 150 to have more durable bridges. And according to the European Construction Industry Federation, the 60% of these bridges already show problems related to reinforced bars corrosion due to concrete aging. So this gives you another idea about the kind of problem we need to face. What about China, the country where I'm working from 15 years? The number of bridges is not so far from the European one. It's more than 900,000. And the average age of bridges is much smaller than was in US, but even if they have mostly been built in the last 20, 30 years, the proportion of structural deficient bridges has already surpassed the US. And it's becoming really a big problem also in China. What about Mexico? Of course, you know your country better than me, but from what I know, the Mexican bridge management system reported that over the 60% of the 8,000 existing bridges on non-toll highways have been in service for more than 30 years. So also in Mexico, I suppose this aspect of aging of existing bridges is becoming very hot. And from the other side, the average daily traffic is growing up. And so, of course, this is strictly correlated to the accelerated deterioration of bridges across the country. So new solutions are needed to improve bridge sustainability and extend the service lives. If we go a little bit inside the problem, we know that the concrete, this material that when it was started to be used, we consider it as very, with a very long time, with no problem durability, but after we realize that there can be degradation of the concrete due to mechanical, physical, structural, chemical, biological, or also due to corrosion. So entering a little bit inside the corrosion reinforcement, it can be due to carbonation, to stray current, but also to the attack of chlorides. So we will show only something related to this kind of corrosion. And the corrosion reinforcement, of course, has a big influence on the load-bearing and survivability performance. Of course, there is this phenomenon of the cracking in the concrete, and so the concrete integrity is influenced. There is a bar section reduction. There is a bond deterioration. But also, and this is very important, the steel bar properties are going to change due to the corrosion, and there is a loss of ductility of the material. The corrosion, and also this one is really well known, can be due to the uniform corrosion, so the cross section is going to uniformly change, but there can be also the so-called localized corrosion or pitting corrosion. So there is a reduction of the cross section area, and so if there is a reduction of the cross section, of course there is a reduction of the rebar strength, but also the concentration of the deformation in the deepest notches that are called pits, so it's due to the pitting corrosion, reduce the global ductility. And these things not only influence the strength, the ductility, but also the buckling resistance of this section. And if we consider, of course, the reinforcement in compression, this is a very important aspect during, for example, an earthquake. I told you regarding the ultimate strain reduction. So it's well known, starting from study that have already more than 20 years, that severe corrosion reduces ductility. You can see from here, from these diagrams, that this is, for example, a severe corroded specimen, and you can see how the ductility and also the ductility is influenced. But also the presence of localized corrosion, the pitting corrosion, influence the dispersion in the ductility. And this is, of course, very, very important. If you have very dispersed results, of course, you need to consider this aspect. We have also with Professor Humberto Varum. Tomorrow you will have his presentation. We and some colleagues in Pakistan, Professor Masood Rafi, we have investigated this kind of problem, try to find some law for these kind of problems.
Esos son los puentes buenos.
But regarding this problem of the ultimate strain reduction, we have also proposed to give an interpretation. Now we'll not go in detail, but you can find all the reference if you'd like in some of publication, my publication in structural concrete. And we tried also to develop a cycling model for the steel reinforcement, able to consider the buckling effect and also the effect of corrosion. And we consider the local buckling that can happen between one stirrups and the other stirrups, or also the global buckling that, of course, involve more than two stirrup transverse reinforcement. But let me a little bit introduce this framework we have proposed for assessing the cyclic behavior, corrosion damage, reinforced concrete bridge column. The idea is to link multi-physic software. In this case, we use COMSOL. Probably some of you knows this software. And to do all the simulation regarding the durability of the steel reinforcement with this nonlinear multi-physic software. And after to do the structural simulation using a software, a finite element software. In this case, we use OpenSys, but also other softwares, SAP 2000 or what you want can be used. In the COMSOL software, the chloride ingress in concrete was simulated as a diffusion process, and we consider the effect of temperature, humidity, corrosion-induced cover cracking, and concrete aging. Now, I don't want to enter in detail regarding the detail of the software we implemented, but only to give you an idea, the chloride ingress is approximated as a diffusion process according to the Fick's law. After we consider the influence of external factors as temperature, the relative humidity, the cover crack width, and the concrete age. Also, this one we took formulation from the literature, so there is nothing of new. We consider also the heat transfer and moisture ingress as using the Fourier law equation and using a diffusion process. Sorry to go faster, but I think we are entering a little bit too much in details. And after, in this way, we can estimate the corrosion current density. This is a law that has more than 20 years. We are also trying to develop a new law based more on data analysis, but the very big problem is that actually there are not so much data to be used. So we need more data. And we consider the generalized corrosion, but also the pitting corrosion. And this is a way how we approximate the effect of the corrosion. There are different methods to approximate the geometry of the pitting, but we use this one because for us it's accurate enough, and in the meantime not so complex to be implemented. And after we did a parametric analysis considering different possible corrosion path. So we did not consider only the generalized corrosion, but also the localized corrosion, and we consider that the worst condition could be the formation of one pit in the middle between two stirrups, and after a high probability to have a pitting on the stirrups location. And regarding the dimension of this pitting corrosion, starting from the literature, we did some hypotheses of the pitting factors, and also regarding the dimension of this pitting. But let me go to a case study only to show you what are the results you can obtain. We consider a typical Italian bridges built in the 70s. So it's always done by two columns, like this one, a transversal beams, and after it can be simply supported, or it can be continuous bridge, maybe with a link slab linking one deck to the next one. So for example, in transversal direction, the bridge can be considered as a cantilever beam, and we implemented this OpenSys software, this OpenSys model, considering also the strain penetration and all the effects that can happen. And we consider, at the beginning, we would like to see what happened considering different scenarios of corrosion and different construction years. So we consider the bridge after 50 years from the construction, 75 years, 100 years. We consider to apply some earthquakes, and we would like to see if due to the corrosion there can be buckling or not. And we obtain interesting results because we obtain that only in one configuration that we consider, so the one associate to only one pitting in the middle with a severe pitting factor, so 8, and in dimension of a pitting of equal to the diameters of a steel rebars, so the dimension is the length of the pitting, sorry, this one. We obtain that you can have buckling even if you are still in the elastic phase. For all the other case, you enter before in the nonlinear phase, and after you can have buckling of the rebars, of the longitudinal rebars. And what we found is that the stiffness of the transverse reinforcement, the transverse reinforcement is fundamental to avoid the buckling of the longitudinal reinforcement, is lower than the required stiffness needed to avoid the local buckling after about 86 years, 84 years, or 75 years for longitudinal rebars diameters equal to 20, 24, 28. These are the reinforcement usually used in bridge column at least in Italy. So after 85 years, it means that I mean, you could have not so much problem of buckling of the longitudinal rebars. What you obtain is that due to the aging and to the corrosion, the ductility of the cross-section is reduced. You can see, for example, at the beginning, the ductility is quite good, but after with the green, that is this one, you can see that the hysteretic curves is influenced a lot. And we also find some link between the yielding displacement considered after 70 years, 50 years, 75 years, 100 years, and the bearing capacity. It seems there is a linear correlation. So the lower is the capacity due to the corrosion after 50, 70, or 100 years, the lower is the yielding displacement. But regarding the ultimate displacement, and this is very important also to give you the idea of the ductility of the cross-section, there is not a clear correlation regarding the type and the time you consider and between the capacity and the ultimate displacement. This is also due to the possibility to have buckling or not in the cross section. Of course, the buckling doesn't give you the possibility to arrive to the ultimate capacity of the cross section. So, to summarize, a computational framework that combines COMSOL multiphysics and OpenSys to assess the time-dependent cyclic response of reinforced concrete bridge columns under chloride-induced corrosion is proposed. It can be quite time-consuming to simulate everything in COMSOL. So we are also thinking to have a mixed system where some phenomenon are simulated in COMSOL and other one are obtained through a data-driven simulation. So having many data, you obtain some law and you use that analytical law and you don't consider all the phenomena in COMSOL. So to try to have a easier way to do it. And also we try to parameterize the corrosion patterns in terms of both localized and generalized corrosion. And this was done mostly based on engineering consideration. And this is, from my point of view, really important. So we need to do research, to go in depth, but never to lose our engineering knowledge. And the behavior of bars are strongly affected by the corrosion pattern. And under compression, the pith arrangement, so the localized corrosion is more important than the pith length and the generalized corrosion. It means where will be the localized corrosion is more important than its length and where it is. And this aspect are quite important, give you also the idea that we still need the research on this topic to give general rules that can be applied in engineering practice. And as I told you before, we are really interested to try to develop some alternative method to the incremental dynamic analysis, the so-called IDA, that is used a lot actually in the assessment of existing bridges. And for us, it's very important to work on the pushover analysis. We try to propose an efficient yet accurate procedure for the seismic assessment of reinforced concrete bridges subject to chlorine-induced corrosion. So we propose to use the incremental modal pushover analysis as an alternative and less computational demanding approach to nonlinear dynamic analysis. That is a very good techniques. It's also influenced by the scaling factor, and also we do not have so many register input at the high intensity. And it's also a little bit computational demanding. So it's why we propose, we call it IMPA beta, and it requires to perform a incremental modal pushover analysis together with an incremental uniform pushover analysis, and after to derive a univocal capacity curve that is an envelope of the results you obtain from the incremental modal pushover analysis and the uniform pushover analysis. So we applied this kind of analysis to a typical irregular bridge. This is a four-span continuous bridge that was considered as benchmark, I think, starting from a US-Japan, European Japan workshop on bridge engineering of, I think, 30 years ago. You see the piers are 140 meters tall, 7 meters tall, 21 meters tall, so typical irregular bridge. And we consider different scenarios for the corrosion of the longitudinal bars and the spiral, and these were obtained using the same simulation done in COMSOL that I showed you before, and considering different dimension of a cover, 50 millimeters or 20 millimeters. Why? Because from our engineering practice, the cover used in the 1970s, for example, was limited most of the time around 20 millimeters. And only recently, at least in Europe, we start to use a largest cover. And here you can find some moment curvature curves obtained considering no corrosion or corroded bridge with a cover of 50 or 20 millimeters, showing how it influences the moment rotation, the moment curvature curves. We compare the results obtained with the IMPA beta with the one from IDA to see if we obtain the same results, and the results were similar. Of course, there are some differences, but related to the different characteristics of the simulation, we can see that they are consistent. And also you see the capacity curves for not corroded or corroded bridges after, for example, 75 years, and how it changed. Going to conclusion, we can say that this IMPA for bridges, the incremental modal pushover analysis, gives results that are that match the results obtained with IDA, even in the case of severe corrosion phenomenon. We only obtained some difference in the deck displacement, but for seismic intensity levels greater than the design condition. So we think that this method can be used. And as I told you also before, we tried to simplify the multiphysics analysis, and we think that the effects of temperature, humidity, and aging can be considered using physical-based models, for example, using COMSOL. They can be simulated in COMSOL, but for considering the cover cracking, they can be simulated with data-driven. It's what I already told you before, that it's needed to simplify, to obtain, to have a possibility to simplify the procedure. So the analyzed case also demonstrates that if we consider an irregular reinforced concrete bridges with severe pitting-induced corrosion, if it's designed with model standards, in Italy, this means in the last 20 years, then the long-term reduction in capacity in terms of base share is limited. What is very important is the reduction not in capacity but in ductility. So the presence of corrosion largely influences the ductility, and we know that is a very important issue. So the question is if the corrosion influences the ductility, and the ductility is mainly due, in this case, from the corrosion of the longitudinal reinforcement. How can we solve these kind of problems? Do we need to change the longitudinal rebars? And if yes, how can we do it? Because if you need to go in real cases, if you have a bridge, you need to go to the column and you need to change the longitudinal reinforcement. This is time-consuming, very expensive. So what can be done? So we enter in the next section that speak about the rehabilitation of reinforced concrete bridge columns using ultra-high performance fiber reinforced concrete. Now in the bridge community, the ultra-high performance concrete are becoming very, very popular. We are speaking about material with a strength larger than 150 megapascal, with a very low water to cement ratio, and that they are very, very compact. They have very also good durability characteristics. And as I told you before, this attract me and my research group a lot. So the possibility to have a material with very high durability characteristic. You can immediately argue regarding the cost of this material. Yes, it's still very expensive. For European price, it can be 3 times the normal concrete, so really very expensive. But this cost can be reduced, or what we are trying to do is to propose a way to reduce it. For example, using a good alignment of steel fibers. You know, this material, fiber reinforced material, and there is a big need to develop a method to align the fibers. So in this way, you can reduce the quantity of the fibers, and so you can obtain a cheapest material. We are working a lot. We have proposed some methods to do it. And if you are interested on this topic, we can discuss about it. So in this case, the idea is to restore the strength, stiffness, and utility of the original column in a short time. So this is very important, the time of restoration. Yesterday, Professor Ayala introduced us the concept of resilience. So this is very important to go back to the starting characteristic of a bridge in a short time without altering the cross-section dimension. And this is also very important. Most of the intervention proposed in the literature, they propose to have an increment in the dimension of a cross-section of a column. In many cases, at least in Europe, this is not possible because there is a street very close to that, so you cannot increase the cross-section. Another very important point is that is the increment in the capacity, I mean the strength of the bridge column. For us, this is not always a right way, because if you increase the strength of the bridge column, in meantime, you need to strengthen the foundation, because this force after they go to the foundation. So they are strictly correlated. What is can be much more important is to have good ductility. So this is the concept why we develop the technology I'm going to show you. And we started this analysis, this proposal, analyzing the bridge column damage after the earthquake. And we also propose to extend these techniques also for high corroded bridges. So here you can see some imaging. This is your bridge column. So we consider 2 cases. I repeat, one, that this bridge column is damaged after an earthquake. So you can have that the concrete is damaged, and also the exterior bars are yielded or buckled, and you need to change that. But also, as I told you before, if you have high corrosion in the longitudinal rebars, and you want to have again a high ductility bridge column, you can use the same technology. So at the beginning, you can remove the concrete in the cover. You can leave the core concrete, but usually it's less damage. After, you can use some connectors that are very simple angle, steel angle, this one, and you can put another steel reinforcement. This steel reinforcement can be properly machined in the center, so you reduce the cross section of these longitudinal rebars. In this way, you are sure that the plastic hinge is concentrated here, and you can obtain a good ductility, because in many cases, when you rehabilitate a bridge column, there can be a problem also of reallocation of the plastic hinge. And this is another problem, another thing that can be, that should be avoided. And of course, we need to be sure that the connection remains elastic. So elastic behavior here of the connection. And we can design the machine and the diameters of a machine part and also the dimension to be sure that the plastic hinge is concentrated here and to have a good ductility of the cross section. We also propose some analytical model to design this kind of solution, and you can find in some of the published papers. Only to show you some pictures, we did it in the lab. We did it for scale piers in scale 1 to 6, but also in scale 1 to 3. Why different dimension? Because we wanted, and it's what we are still doing, investigating the scale factors. That is always a big issue when you go in the lab, but it's something, even if it's a traditional problem, is something still needs to be investigated. So you can see here the connection. This kind of connection was selected after comparing many different other solutions using mechanical connectors or using welding connectors of different kind of solution. We selected this one because, you know, when you go to put another steel rebars and you already have a rebars here, you can have, I hope you see from the camera, you can see that there can be problem with alignment of the existing reinforcement with a new one. So to solve this geometrical tolerance, we consider that these kind of connectors can be very good. And also we asked to different skilled or not skilled workers to do the connections to weld this part both in vertical or in horizontal situation, because in horizontal it's very easy, but if you do in real situation, it can be more complex. And we saw that the results were really better, less dispersed, if we use this kind of connectors. So it was something mixed between some problems of, how can I say, some construction problems, but also technical problems. And of course, we tested it. We saw the test 1 to 6, but I told you we did also test 1 to 3 in our lab in Fuzhou, using this setup and applying this history of displacement that was taken from an earthquake in Italy in 1976. And we also implemented finite element models. As I told you before, I already showed you this kind of models where we consider all the different effects we have with the strain penetration and so on. For the concrete, we consider two different situations because, of course, where you are going to rehabilitate the bridge, the normal concrete in the core is in some way confined by the new ultra high performance fiber reinforced concrete cover. So we consider it this effect. And we also consider the stress-strain relation for ultra-high performance concrete using the Naemi-Mustafa law. So we calibrated adequately the concrete to OpenSys material that we use. If you are using OpenSys, probably you use this kind of element. So we calibrate to follow this law proposed in the literature. Actually, we did many tests on ultra-high performance concrete and we developed our three-linear model. But at that time, we used the one in literature. And we analyzed the same bridge I showed you before, exactly the same one. We consider different dimension of the intervention. So the idea was to investigate how long should be the intervention, I mean, with the ultra high performance concrete. Should be of the same dimension of a plastic hinge, so where I'm going to change the steel reinforcement, or should be longer to avoid the real location, the changing of the position of the plastic hinge. So we were worried that if the intervention, the part of the bridge column where you put the ultra-high performance concrete is equal to the length of the plastic hinge of the part where we change the steel reinforcement with the new one, as I showed you before, we were worried to have a reallocation of the plastic hinge where we do not have the ultra high performance concrete. And so we try to investigate it. We also try to investigate how should be done the reduction of the cross section of the steel reinforcement we are changing. So this is the so-called turning factors. It's something like, I mean, we reduce the cross section in that area. So we consider the time at which the bridge column is repaired once corrosion is started, after 15 years, 75 years, and 100 years. Why did we consider it? This is another important factor. When we rehabilitate an existing bridge, we always do a, how can I say, a photo of the situation of the bridge in that moment. And we try to have a good capacity, to have good utility, and so on. But the question should be not only what is the situation now, but what will happen in 25 years, in 50 years, in 100 years. So is the intervention I'm going to do the best one, not only to increase the capacity in that moment, but to increase to have enough capacity in all the life of a bridge. And this is very interesting because I can show you the results that if you do not consider it, you could do some, how can I say, not mistakes, but something that could have some trouble, some problems. So, for example, let me show you some push cover after 15 years. So I do the intervention. So the column is repair at 15 years. And we do the hypothesis to have a dimension of intervention that is equal to the length of a plastic hinge, or that is twice the plastic hinge. So you can see here that you obtain a very good response, both with the dimension equal to LP or double than LP, using, for example, a turning factor of 0.6. It gives you the dimension of the cross section. So this is 15 years. But what's happened if the repair column is considered after 75 years? You can see that if you do it, it changes completely, because you need to have intervention equal to 2 LP, as you can see here, to still have a good characteristic. So the intervention is influenced from when you do it, and also if you consider the long time behavior of a bridge. And this is also for 100 years. So we also consider, as I told you, what happened in the section at the base, but also what happened in the first unrepaired section, to avoid the formation of a plastic hinge immediately above the intervention area. And we can see that if we do the intervention not changing the steel reinforcement, but only using the ultra-high performance concrete, this is the case, the easiest way. I do not change the steel reinforcement. I only put the new concrete in ultra-high performance concrete. What you can get in that case is that the plastic hinge change the position from the base section to the first unpaired section. So this should be avoided. It's why, now I don't want to, sorry, but I'm really spending a lot of times. I don't want to go in details, but you know, this is very, very important. So the main things I would like to tell you, to communicate to you, is that we need to try to have not only good capacity, but also good ductility. The ductility is linked also to the steel rebars. So you should consider to change the steel rebars to have again good ductility. And the other message is this: it's very good to use this confinement with ultra high performance concrete, but you should pay a lot of attention if the most sensible section becomes the first one above the repair area. And so from our point of view, the best compromise was to use an intervention with ultra high performance that has a dimension of twice the plastic hinge dimension, and to change also the steel reinforcement using a tanning factor of 0.6. Let me introduce you in a very quick way also another very important things from my point of view to extend the service life of bridges. That is the integral abutment bridges technology. In the title, I put innovative material technologies. Yes, ultra-high performance concrete can be considered a quite new material. The concept of the integral abutment bridges is not new. It comes from more than 100 years ago. So it seems in some way during the reconstruction after the Second War, at least in Europe, we decided to do everything, all the bridges prefabricated, simply supported, a lot of bearings, a lot of expansion joints, and after we realized it's very expensive due to the maintenance and the durability problem of joints and expansion joints and bearings. So my question is it possible to eliminate or to partially eliminate this expansion joint and the bearings? And what's the seismic behavior and the behavior of this kind of bridges induced by live load and particularly by the expansion and contraction induced by thermal variation. A typical integral abutment bridge, at least a new integral abutment bridge, is done as this one, so it has slender abutment and an approaching slab. The approaching slab can be supported by a sleeper slab. The backfill can be also supported by some geogrid or something like that. And there is also continuity with the superstructures, something to have a big frame. And after you can have some joints that are far away from the deck, and this helps a lot. In fact, you can have two different approaches. You can have very slender abutment, so when there is the expansion and contraction, the bridge can move. Or you can have very rigid abutment. In that case, the abutment, you can consider them fixed. And of course, the expansion and contraction is avoided, so you can have big forces in the deck induced by thermal variation. If the deck is very flexible, you do not have high stresses induced by thermal variation in the deck. These are two completely different situations. The real situation, of course, is in the middle, where you should consider also the interaction with the soil. So let me do step by step, and the first things is the elimination of expansion joints with link slab. This can be done in new bridges, but it can be also done in the rehabilitation of the existing one. It's something we applied in many cases in Italy, in Europe, but also in China and South Asia. So this is the typical bridge deck, the bearings, the conventional joints. You can use a link slab that link one with the other span. And but this link slab, starting from the work the reference work of Alp Zaner and Paul Zia, we know that this can have some cracking problems, so there are some indications to try to limit this cracking, but still there are some concerns. So in the last year, several materials have been used in the construction of links lab. I told you conventional concrete, they can have cracking problems. So they have been used a lot of fiber-reinforced concrete to limit the cracking, or fiber-reinforced concrete with steel and synthetic fibers. They have been used a lot, the ECC, the engineering cementitium composite. You know, it's a concrete with a low Poisson modulus, Young modulus, sorry. So it can have a very big deformability. And this works quite well. Or also ultra high performance concrete when you need a material that is in meantime with a good strength, but also with low cracking characteristic. And this is what we have investigated in the last year, thanks to the work of my PhD students and our assistant professor, Mr. Lin. And we did many experimental tests considering bending, but also considering axial force acting on the link slab made with ultra high performance concrete, trying to optimize the dimension, how to design the material, how to design the link slab. And of course, we also investigate a lot from the numerical point of view and this kind of solution. We consider not only the link slab between one girder and another girder, but also between the girder and the abutment wall in the case of integral abutment bridges, where you want to limit to eliminate the joint also close to the abutment. And we also propose a precast ultra high performance concrete link slab to avoid the problem to cast on site of this kind of material. And all these things has been published in some conferences, but I hope, I mean, we are submitting some papers also for some journal, but if you are interested, please contact me. We have also applied to some real cases in China. But I told you the problem due to the soil structure interaction induced by thermal loads, so there can be contraction or expansion, and this cyclic load can also induce a separation, a gap between the abutment and the backfill. So this is very important, and why. And this is why an approaching slab here should be carefully designed to be a bridge between the real bridge and the backfill, or we should use other technology, as I will show you before. And also the soil structure interaction should be investigated. This is not something that should be worried about, because it can be also beneficial for the bridge, because it can help the behavior of the bridge. It doesn't mean it's not good. And so how to improve the thermal loads and the thermal loads and seismic performance of integral abutment bridges? One technology could be to use a flexible backfill, so you can separate the abutment wall from the backfill using some very flexible materials as EPS, so it can be really high deformation capacity, and the backfill can be supported using some gel grade, so this can benefit a lot because in this way the backfill is not directly pushing on here. Or you can also use another technology that is piles with pre-hole. Please consider to have a pile, and after at the end you have a pre-hole. If you use it, you increase the flexibility of a pile. If you increase the deformation of a pile, the bridge can be more flexible, so you have less problem regarding the thermal expansion and contraction. From the other side, it can also help for the seismic behavior. Please try to think of the concept of seismic isolation, where you increase the period and so you increase the seismic performances. But this is not enough. As you do in the seismic isolation, you need also damping. So you need to increase, in meantime, the damping and also the deformability. So you increase the period and you decrease the action. This is an old concept. It was also used in some buildings like this one in Auckland, in New Zealand, where also viscous dampers were used. So we don't want to use viscous dampers, but we want to try to have some very cheap material. So starting from the concept of geotechnical seismic isolation, where a rubber soil mixture is used, and you can use the concept to have increase in damping and increase in the period. We also investigate this kind of techniques. Also, we are trying to develop a method to carefully consider the nonlinear behavior of the soil. And so we develop a method where we mix the discrete element method to simulate to obtain the characteristic of this engineering soil with a method that is called Presac formalis to simulate the nonlinear behavior of the soil. This is something in which we are actually working. And we try to use this concept of the pre-hole technology also in YAPS, using a pre-hole and using high damping material, mostly using rubber inside soil rubber mixture of different characteristics inside the pre-hole. Also, this concept is not new. It was studied also by some Italian professors some years ago, for example, Professor De Stefano, and also it was investigated by Professor Milonakis, one of our friends and collaborators from the University of Bristol. We use this concept in this bridge. You see here, it's a bridge in Shenzhen, in the south of China, close to Hong Kong. It's a free span precast post-tensioned bridge, concrete bridge. Each span is 30 meters. And you can see here detail of the cross section. We were involved in the design of this bridge in Shenzhen, and it has concrete piles, so 25 meters long, 1.5 meters of diameters, and it's a fully integral abutment bridge. So no expansion joints and no bearings. We did many tests on scaled and using cyclic test, but we also performed some shaking table tests on our facilities in Fuzhou. We simulated both the scaled test, but also we simulated one-to-one to try to investigate the scale factors effect. We proposed some PY curves that can be used in engineering practice for this kind of work. Sorry, I'm going fast, but I think my time is almost finished, and sorry if I'm so long. We also consider the, how can I say, the effect of the pre-hole on inelastic response of this kind of bridges, and we investigate the different effect of a pile with no damping pre-hole or with damping pre-hole, and using some simplified Winker model, we formulate some probabilistic model using Bayesian regression. This is not so important, and but only to tell you that we try to give some indication that can be used in the design of this kind of bridges. Now, let me briefly introduce also what we have done some years ago inside the Horizon 2020 program with University of Bristol, Roma Tre University in Italy, the University of Porto in Portugal, the University of Ljubljana in Slovenia, and the Technical University of Kaiserslautern in Germany. And we propose what we call it a novel integral abutment bridge. This is the first sketch we did during the first meeting we had in Bristol, where we start to consider to have an EPS between the abutment wall and the backfill. We start to consider to have a backfill with shredded tiles, sand mixture, geotextile. So we did many hypotheses. And what it was interesting from the beginning, we start to consider the possibility to have a pile that is connected to the abutment foot, this one, or not. So it can be also disconnected, so you can have movement between the pile and the abutment wall and the superstructures. And to have also a pile with pre-hole where you can use soil mixture or you can use EPS inside, and you can increase the deformability. So what is the seismic behavior of this kind of bridges? We consider typically European integral abutment bridge in concrete, like this one, and we did the model. We went to the lab, in this case, not our lab in Fuzhou, but we went to the shaking table of the University of Bristol, because these tests were paid by this European project. This is how we use the instrumentation, only to let you understand. We consider different kind of configuration of the EPS, and we consider also to have piles connected or not connected to the abutment here, foot. So the different cases that we would like to investigate. we went to the shaking table. I don't know if you see the video, but in the video you can clearly see that when the earthquake in longitudinal direction arrive, you have a little bit a segment of the soil close to the abutment wall. That is something also show the pressure between the soil and the abutment wall. So we investigated, as I told you, this is the bending strain that we connected. We also investigate the case in the pile with connection or with no connection. So of course the bending strain change a lot in the piles. We also propose a numerical simulation method done in open seas with a continuum approach and adequately considering the boundary condition that in these kinds of simulation should be adequately considered. And this allows us to also to do it in one-to-one scale or reduced scale and to consider different scenarios. This was really important also to compare the pressure on the abutment compared to some models recently proposed also by Marchi and Frankin, and also included in the new version of the Eurocode 8 part 2. In the Eurocode, in the new Eurocode, there will be also a part on integral abutment bridges. And we found that this proposal are a little bit conservative, but as it's also normal for something that should be acquired in a code. So to conclude, the jointless bridges they have improved durability, lower cost associated with construction and maintenance, also improved driving comfort. The response of flexible rigid abutment should be better investigated. We are doing some PhD thesis to show the differences between one and the other. The pre-hole seismic isolation, or this how it's called, geotechnical seismic isolation, can be a promising technology allowing to increase pile dissipation capacity and flexibility. The compressive inclusion, like the EPS, reduce the acceleration of the bridge deck and the segment in the backfill, while disconnecting piles from the cap decrease bending near the pile. We also develop this modeling strategy that seems to work quite well. So, of course, this is only an introduction to the problem, but if you are interested, I'm really, really happy to collaborate with you. To finish my presentation, I want only to tell you what I already told you at the beginning of my presentation. So why we are using, and we in the last decades, we put so much attention to develop reliable seismic hazard maps, but regarding the corrosion, we still use some how can I say, some simple indication. Can we do a step forward to develop, how can I say, a next generation of performance-based design using probabilistic corrosion of that map? This is what we try to do. So to extend the performance based design approach in use within modern codes to durability issues. So we did it for an island, for the Hawaii Island in the United States, not only because probably they are nice, I have never been sincerely there, but because to do it, to develop this corrosion hazard map, you need some data. And these data were available for this island, and so we did it for this reason. Which data you use? You need data regarding the sea waves and salinity, the temperature and humidity, the rainfall and wind, and also the chloride deposition rate. And these data regarding the chloride deposition data rate are not so common. You can use it through the wet candle method, and but you need to put along in some places. It's not so expensive, but in meantime, if you don't do it, you cannot get these kind of structures. It's the same with seismic hazard map that we need a lot of data to do it and a lot of sensors, of course. So we consider this island. I told you we analyze also, only to give you the idea, the bridges existing in the island. They are mostly on the coast. And what they did is to measure the chloride deposition rate exactly the chloride deposition rate exactly along the coast. So why? Because they did it following the bus station. They put one in each bus station. And so we analyze the sea waves, the temperature, the wind speed and direction. I told you the chloride deposition rate that we obtain and we analyze. And from this one, we could develop some hazard map considering a probability of exceedance of 2% in 50 years. And this is for 70 years, this is for 100 years, and you can see different probability and different hazard. Of course, to do it, you need also to do some hypotheses regarding the cement content and water to cement ratio. We did this one because in this way we could get some data from some analysis done in Brazil by some other authors. And only for that reason. But what we want to show is that it's possible to develop this one. Probably they need to be improved, but if we don't start, we will never improve them. So to conclude, coastal areas are one of the most active zones on the planet. As for the 2010, the share of the population of coastal regions living within 5 kilometers from the sea was 34% and 45% in Italy and Spain, and 45% in China. And so the corrosion hazard map would be a meaningful tool for the proper management of existing construction on one hand, and also allow to elaborate more rational design rules for the durability of new construction on the other hand. These are my main conclusion, but they only summarize all what we have seen before. So it's a summary of all the conclusion I did before. So I think we can also shift them and go to the discussion phase. And I'm very sorry, probably I took too much time, and I'm sorry for these things. Hello?
Thank you, Professor Bruno, and thank you for your excellent and motivational lecture. We will continue with the question and answer session that will be conducted by Professor Ayala. So go ahead, please, Professor Ayala.
All right. We in the session we had four questions, and I'll take the liberty to read them. First, do you consider functional steel in bridge construction with polymers reinforced with carbon fiber, glass fiber, or basalt fiber to prevent corrosion? That's the question. Did you get it?
Sorry, may I ask you to repeat because the connection was not so good?
Do you consider it feasible to replace conventional steel and bridge construction with polymers reinforced with carbon fiber, glass fiber, or basalt fiber to prevent corrosion?
We did not work too much on this topic, but yes, there are some colleagues working on it, and I'm collaborating with some professor in Canada, and they are doing many research on this topic. As you know, they have really extreme environmental conditions. They did it, and it can be an alternative solution. We think that other materials as ultra high performance or fiber reinforced concrete, they do have a lot of advantage and can have, particularly in the next years, a very promising application and in some way overpass some aspect of the use of carbon fiber, glass fiber, that are very, very good materials, but in meantime they could have some issue related, for example, to the behavior with the temperature, or they can have some issue linked to the bond. So yes, of course, it depends case by case, and in some cases, I fully agree that they are a good solution. It's important when we design something new, bridge, or the rehabilitation of existing one, to have different choice and not to go directly to one, because from my point of view, at least from my experience in Asia and in Europe, case by case, one solution could be more efficient than another one. what is really very important is, as we discussed during my presentation, is to consider all the lifetime of structures to select the best solution. Of course, related to all of the also the cost consideration that can be different country by country.
All right. We have another questions that says, what can we change on new bridges to prevent these problems in the future? And how long will damaged bridges be usable? Is there an estimate?
Yes, related to what we can do for the new bridges, of course, the first things we should evaluate is to use material with long performance. But materials are not enough. We need to have a good practice. And unfortunately, what is happening from my point of view in many countries, particularly in Italy, but also in China, so I'm telling what I see in my personal experience, but I was lucky to take part to some project in several countries, is that bridge engineers are becoming day by day more some people that are only doing calculation and they are not putting attention to the concept of structures they are designing. So this is particularly important, and it's something we should start to discuss again and again. So to discuss more about the conceptual design of building, but also the conceptual design of bridges. When the bridge is designed, the concept of the bridge is wrong, after you will have always problem with durability, but also with extreme event. So it's something linked also to what Professor Ayala showed yesterday. It's not only to design a section with the right amount of concrete, of steel, and so on, but is to do a step below to think a little bit, is it the concept right or not right? For example, many people are arguing that integral abutment bridges are not a good solution for curved bridges. They consider that only if a bridge is straight, okay, you can use an integral abutment bridges. But why? I always don't understand it, because if it's a curved bridge, when there is the temperature, the bridge can in some way escape horizontally, and the forces that you have on the abutment are reduced. This is also something investigated by one of the students of Professor Schleich in Stuttgart, I think 40 years ago. So what you need to do is to design in the correct way the horizontal stiffness of the deck, in that case, and the stiffness of the piers that should allow the bridge to move in the transversal direction. So now we are introducing new material, for example, ultra-high performance material that is completely new material. And we are using in a very traditional way. So my question is, are we using the right way for this material? I'm not so sure. I'm not so sure about it. A lot of things can be done, but if we do not have a clear idea about what we want to, about what we have, where we want to go, from my point of view, we are really realizing a not sustainable solution. And this is very important. Also, the artificial intelligence that was yesterday introduced and explained us in a very high-level way in the lectures of Professor Ayala. From my point of view, it's a big chance because it can give us the time to concentrate on the concept, on what engineers should do. Sorry to discuss about this point, but because from my point of view, it's a discussion never done inside the classrooms and never done between colleagues. We like more concentrate on details that are particularly important. I like details, but in meantime, we need to start also to discuss about the concept of a bridge, concept of it depends case by case. I think new material and new technology offer us a lot of chance to increase our the sustainability of the next generation of bridges. In meantime, we need to start to use them and not they are the thinking part of the project. The thinking part is still inside our mind. I hope so, at least.
All right. I will concentrate in giving you one question per each of the interested people and see how the time goes. Yeah?
Sorry, can you repeat?
So I will give you some other questions.
Yes.
And you tell me which one you can reply within the reasonable time. Juan Lopez says, are concrete additives currently being used in Asia and Europe to protect reinforced steel from corrosion in new bridges?
Yes. I think in new bridges, we are, of course, carefully design the cover and that's really important. In some important bridges, we are using no corrosion steel, but this is still considered quite expensive. It's well known the use in the Hong Kong-Macau bridge, the connection between Hong Kong and Macau, where a lot of inox reinforcement steel, inox steel in the reinforcement for the reinforcing bar was used. So it's a good solution, but in the meantime, you should consider the cost of this kind of solution. There is a little bit push in very important project to use it. It can be also a mixed solution. So close to the cover, you use inox steel, and far away, so in the center of the cross section, you use normal steel. But still, how can I say, the correct design of the cover is the most important things. And sometimes corrosion is also linked to detail, because of course, if you do not design the detail where in some joints, where many reinforcements are arriving, so in that place, it's the casting of the concrete is not so easy. And so even if you theoretically you did a good design of the cover, you follow all the rules, after in construction site, there can be many difficulties. And so it's not only related to the strictly application of the rules, but also to design in the correct way the joints. And this is due, of course, there are many line guides, but it's also due to the knowledge of the company where you are working, or your knowledge. I don't know if I replied to this question.
I think so. I think so. Is there any evidence of the effectiveness of these approaches?
Yes, I mean, regarding the correct design of the steel reinforcement, also for improving the resistance, there are amazing examples of bridges designing in the 60s, in the 70s, that are not so much affected by corrosion. So even if they are in the same place as ours, it's not only due to the concrete. Of course, maybe the concrete could be a little bit better, but it's also due to the selection of how the designer select also the reinforcement. But from the other side, regarding the use of the right cover, there are many studies regarding it. Regarding the use of inox, there are many studies regarding it, and also regarding the use of ultra-high performance concrete that, as I told you, can be used only in some part of the bridges. So there can be hybrid solution where I use normal concrete, where I do not need high durability or strength, and I use ultra-high performance concrete only where I need. And I think this is the most promising actually solution. So you can reduce the cost of the total cost of a bridge, because you use the ultra-high performance concrete only where you need. In meantime, you can get very good performances, long-time performances and short-time performances. So this hybrid solution, I think they are really very, very good. And it can be also a hybrid solution with steel and concrete, and using ultra-high performance concrete as the concrete material. So steel element plus ultra-high performance concrete. This is also really hot topic in China, and also already applied to some important bridges in China.
All right, thank you very much. I think we have 4 other questions, and I suggest we keep them, and I will let you have them. And if you could please send it to me by written, some answers, and then I will transfer this information to whoever is interested on it. I think due to time restrictions on this thing, I pass the word to Professor Haro so that we can actually get to the final conclusions of this very, very nice presentation. Thank you very much.
Thank you. Thank you very much. And I thank all of you. Sorry, I'm very sorry because, yes, I took too much time, and after we did not have so much time to discuss. So I'm
Not to
very
be sorry, it was very interesting and we appreciate it very much. However, we have some restrictions about the duration of the event. Jose Manuel, are you?
Yes, I'm here.
All right.
Thank you, Professor Ayala. Muchas gracias, Profesor Ayala. Just to finish again, thank you, Bruno, for your excellent lecture. I think everybody liked it. And we hope to see you for an in-person lecture in the near future in Mexico. So I just have to finish presenting the conference, the lecture we will have tomorrow. Para todos los que nos acompañan en esta transmisión, ya vamos a terminar, el tiempo se nos ha terminado. Voy a nada más a darles información de la conferencia que tendremos el día de mañana y que terminaremos posteriormente el simposio con una mesa redonda. El día de mañana platicará el profesor Humberto Varum de la Universidad de Porto en Portugal. El título de su conferencia es Diseño sísmico de edificios de concreto, lecciones de temblores recientes, reglamentos y resultados de investigación. No obstante que en la información que se circuló a través de todos los medios del Instituto de Ingeniería y de la Universidad Michoacana, el título de esta plática está colocado en inglés. El profesor Humberto Varum habla perfectamente español, de manera que accedió a dar su plática en español. Posteriormente a esta conferencia del profesor Humberto Varum, tendremos una mesa redonda donde estarán participando también los conferencistas de este simposio. Por lo tanto, los invitamos a todos a que nos acompañen el día de mañana a partir de las 4 de la tarde. Tendremos la conferencia de 4 a 5 de la tarde y de 5 a 6 de la tarde estaremos con la mesa redonda. Gracias a todos por asistir, and thank you very much, Bruno. See you tomorrow, all of you.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. I will be sending you the questions by an email.